Hi again, everyone. Today we're going to talk more about bivariate distributions. Last lecture we talked about the case of two discrete random variables, so we saw things like the joint probability mass function, or you could call that the bivariate probability mass function. And we're going to finish that discussion today by showing how you calculate expected values for functions of two random variables. And then we will move on to the case of continuous random variables. So we'll introduce the joint probability density function and marginal probability density functions and conditional probability density functions. And so we're basically trying to extend what we did in the last lecture to the case of continuous random variables. All right, let's get started. So what we want to introduce here is expectation values and how you compute them. So expectations. And this works very much like it does in the case of one variable. So we can generalize pretty easily. So we'll just jump right into the definition. And we're going to define it just in general, not for any special circumstances. So let's say you have two discrete random variables, so we'll call them x and y. They're discrete random variables. And let's say we have their joint PMF. So with joint PMF. There we go. And then let's say we just have some arbitrary function of these two variables. Say, all right, so say then let g of x and y just be any function. I should say then for. Let's rewrite this. Sorry about that. So for any g of x and y. Sorry about that. So for any g of x and y function, its expected value, the expected value of g, is going to look just like it did in the case of univariate random variables, except we sum over the two different allowed values for x and y. And so we put in the value of the function and then multiply it by the probability mass function. Yeah. And again, we're using that shorthand notation where the index of x on the sum means the sum over all possible values of x for which the probability mass function is non-zero, and likewise for the y sum. All right, let's try a little example and see how this thing works. So again, we'll just make a table. I think this is one we've used this before. I might need a little bit of space. I'm going to move this over here. So I'm going to introduce a table of the probability mass function. And we've actually used this particular example before. So let's say y can have values of 1 and 2, and x can also have values of 1 and 2. And we're going to use the following function. So I think we've introduced this before. It's going to be x times y over 9 for x and y in set 1, 2, and 0 otherwise. So we already used this thing before, and we constructed this whole table before, but we can do it again. So when x and y are both 1, this is a ninth. When x is 1 and y is 2, this is 2 ninths. And this guy is 2/9 as well. And when they're both 2, it's 4/9. And we're going to use the marginal distributions. And so I'm going to fill in that part of the table. And just like I did before, I'm going to use a different color for that. We'll use black again. I think it's handy to do this when you can. And this is a pretty easy case, since there's only 4 different values here. So if we were to sum in this direction, sum over the y values, then we would end up with the marginal distribution for x. And if we do that, the first one, so when x is 1, this is 3/9, which is a third. And if we do the second row, when x is 2, that's 6/9, so 2/3. And this thing is symmetric, actually. So when we sum down vertically like this over the x values, so there's no more x dependence, we end up with the marginal distribution for y. And it's the same, so a third and 2/3. That's because this probability mass function is symmetric about x and y. And of course you can do this thing, I don't know if anyone ever does this, but you can check that they add up to 1 properly, and you're in good shape. Alright, so that's just laying out the probability mass function and all the information that we have. So let's say the first task for us is to find the expected value of the product x times y. So let's make that problem 1. So find the expected value of x times y. Alright, so we'll just go straight into the definition. Oops. Right, and so there's a sum over x. And we know the values here, so we can put them. Eraser's gotten kind of big. So we've got x is equal to 1 to 2. And the same for y, we have it equal to 1 to 2. Otherwise you would get 0. So these are the only non-zero terms. And then we put x times y, the value of the function that we're interested in, and f of x, y. This is a little bit redundant. I could have left all x's and y's there. The f would then clip it, because the f is 0 when x and y are outside of the allowed range. But nevertheless, that's just a little redundant. So we'll keep that up there. And we'll put in f. F was in that range of x and y, it's x times y over 9. And so what we have is just 1/9 times x squared y squared. And then we just write this out. So we've got 1/9. And I think for me it's easiest to look at this as a matrix. So you've got row 1, column 1, row 1, column 2, and so on, and just keep all the terms. So at row 1, column 1, so x is 1, y is 1. This is 1. So let's just write it out. 1 squared times 1 squared plus 1 squared times 2 squared plus 2 squared times 1 squared, and then plus 2 squared times 2 squared. Yeah. All right, so that's it's not a half out in front, that's 1/9. Okay, so we have 1/9, and then what do we have? 1 plus 4 plus 4 plus 16. So that's 25/9. All right, so that's the expected value of the product of x and y. Now let's say we have a second question, number 2, and we want to find the expected value of x. Okay, so again we're going to go with the definition here. Now here, there's no real new definition here. I think in the notes you'll see after the expected value is shown for functions of x and y, they'll just remind you what the expected value looks like for x, but it's not any different than it used to be, except that we put a subscript under the f for some reason. So this guy looks as follows. So the expected value for x is the sum over all possible values of x, where it's non-zero, where the PMF is non-zero, and then we put the value of x and then the probability mass function for x. But if we're building, we don't yet have the probability mass function for x all by itself. We're going to build it out of the joint probability mass function. So we put a little label underneath it like that, kind of just to remind us where we got it from once we get it. It doesn't have any new meaning, really. X is still just a random variable, and this is its probability mass function. And so I'm going to go over here and look at what it is. So we've got two different values for it, 1/3 and 2/3. And so we can just write this out. So this is 1 times 1/3 plus 2 times 2/3. So that's 1/3 plus 4/3, so 5/3. And I think you could also work out, if you wanted to, you could find the expected value of y. And in this case, you can just see it, because if you go back up here and look at the probability mass functions, it's completely symmetric, right? So this row looks just like this, and the matrix here is symmetric. So everything would work out exactly the same. You can go through the steps, and this becomes also 5/3. And it's sort of interesting to point out, so I'm just going to put on the side, notice, in this case, the expected value for x times the expected value for y, it's 25/9. This happens to be equal to the expected value for x times y. Now that is not always the case, and we'll discuss that in the next lecture. But it's worth noticing that it was the case here. All right, so now we're going to move on to continuous distributions for the bivariate case. So this is bivariate continuous distributions. Or maybe you want to say continuous bivariate distributions. I'm not sure what you might want to say. And we're going to start off with joint probability density functions. And the material that we're introducing here really just follows the same roadmap that we did for the bivariate discrete distributions. So we're really just going to kind of do the exact same roadmap. The definitions are a little different, though, obviously. Right, so we're just going to jump right in and make the definition of the joint probability density function. So we're going to suppose that x and y are both continuous random variables. So let x and y now be continuous random variables. Right, and then let's say, so what we're interested in is we want something like the probability density function, right? So I don't know if you remember this, but the probability density function for the univariate case, so like for one random variable, one continuous random variable, it's called a density because it's sort of like a probability per unit length, right? You have to multiply or integrate over some length to get a probability out of it. And so we're going to do something similar here, but we're not going to be looking at just lengths. We're going to be looking at some region in x and y space. So not just some interval in x, but some interval in the two-dimensional space of x and y. So let's say you've got some region. So then for any region, and I'll call that region T, right? So let's say this is a subset of R2, so the two-dimensional space of real numbers, or I don't know what you want to call that thing. I forgot what mathematicians call it, but R2. Then the following statement defines the joint probability density function. So we'll say the probability that x and y are in that region, are in T, is given by the following integral. So we've got integral over x, integral over y, but both of them are such that you stay in the region T. Then we put the probability density function here that we're just about to that we're just defining this thing. And dy. Right? Sometimes people don't bother writing multiple integrals like that. And also, I don't know if you've ever seen this notation, but I like it a lot, so I'll use it a little bit. So this is the same thing. This is just another notation for the same thing. Like that. And this is, I think you might not be familiar with this notation where you put the entire integral operation to the left. So I'll just mention kind of how it works. So you act on things to the right like that. So this thing, the like syntax, I'll just erase this in a second. So this like operational syntax, or rather operate to the right, like just the same way that like the derivative does. Right, so if you put d dx next to something, you know that it acts on the thing to the right. That's how most operators look, actually, and so I find this notation a little more convenient. You can use the old style notation if you want. So I'm going to erase this little definition here, but you might want to keep that. I guess I could just leave that there. All right, and so this thing, the name, so f of x, y, is called the joint probability density function. For x and y. All right, so that's just the definition. Right, there we go. All right, so what you want to think of here, if you think about what this integral is, f of x and y is like a surface, right? So this is just an aside. Right? So the surface f of x and y is like a probability per unit area. Per unit, I guess you want to say xy area. And just like you had probability per unit length for one-dimensional probability density functions, and you got probabilities from them by either multiplying or integrating, rather getting the area under the curve, in this case, you get a probability, so you get a probability from volumes under the surface. So hopefully that sort of makes sense to you. We can work out some examples and you can see how that works. But you can see it actually straight away just, I think, a little bit at least, from looking at the properties. So let's look at the properties of this guy. So properties of joint PDFs. So these are really requirements, just like they were in the case of univariate cases. So the first one is what we call positivity. And so this says that f of x and y always has to be bigger than or equal to 0. So this we named this positivity. And then the second one is honesty. But the honesty condition looks a little bit different here because, again, you get probabilities by adding up the volume underneath the surface, right? And so that's going to look like this. Integral from minus infinity to infinity. And then we've got another one. So one for the x dimension and one for the y dimension. Like that. So that total integral, so this is all of the volume underneath that surface for the entire, in the entire xy plane. So between that surface and the entire xy plane. That's all the probabilities. So that's got to add up to 1. All right, so those are our two conditions. Let's try a little example. We can work out some actual probabilities. And this example, we're going to be using it over and over again, or at least we're going to use the probability density function that we get over and over again. So it's good to pay attention to this one. So let's say we've got x and y are both continuous random variables. And they have a joint PDF. It's a relatively simple one. Let's write it down. So we've got f of x and y. And it's equal to, in the interesting region, it's equal to k times x plus y. So it's a pretty simple function. And so this is for x is in the region 0 to 2. And y is in the region 0 to 3. So slightly more space there. And then otherwise it's 0. So this is just a really simple surface. And so here k is a constant. So for constant k. And the first thing we're going to do is work out the constant. All right, so that's the first challenge for us. So find k. All right, and so as you can imagine, we're going to do this with the honesty condition. So we're going to insist that 1 is what you get when you do the integral. And so I'm going to use that notation that I described to you before. So the x variable is going to go from 0 to 2. I'll put dx here to remind myself of that. And the y variable is going to go from 0 to 3, dy. So I hope this notation is maybe I hope you'll find it interesting. It's useful. Like that. And so the first thing we're going to do is we're going to take this integral and operate on the integrand with it. And then after that, we'll take the result and we'll take this integral and operate to the right with it. So let's go through with this. So the x integral just sits here while we deal with the y integral. And the y integral, these integrals are easy enough. So we've got k, nothing happens to k. So when you integrate x from 0 to 3 in y, you just get 3x. And when you integrate y from 0 to 3, so let's see, you get 1/2 y squared. But y, so I'll write the y squared for a second here. But y, it goes from 0 to 3. So when you put 0 in there, you're going to get nothing. And when you put in 3, you're going to get 9. And so I'll just fix that up. So 1/2, 9. Like that. So there we did the y integral. Now we have to do the x integral. Right? And so this is k times 3 and then times 1/2 2 squared. And then when you do the x integral over this constant 9/2, you just get 9/2 times 2. So that's the length of the x integral. All right, so this is k times 6 plus 9. Or rather, 15k. Which tells us that k is 1/15. And so that tells us the constant k. Sometimes that k is called a normalization constant. I should mention that up here. Or, I don't know, maybe people might call it like an honesty constant or something like that, but it's a constant you get by enforcing the honesty condition. And so we could go back, so this is what our probability density function is going to look like, just with k is equal to a 15th. And we're going to use that for, I think, most of the remaining examples that we have in today's lecture. All right, so let's look at the second question in this example. So we want to calculate the probability that x is smaller than 1 and y is smaller than 2. So x smaller than 1, that's all the places that x, is that all the places? I've forgotten. No, x can be in up to 2 and y can be up to 3. So this is some limited region within the values that x and y can take on and get for non-zero probabilities. All right, and so let's just work this out. So the probability, I think in the book they do, or in the notes they do y equals 1, but I think it's too boring, it's too simple. Everything is the same, you can't see anything different happening. That is to say, you can't tell the difference between the two variables. Okay, so we're going to say x is less than or equal to 1, and y is less than or equal to 2. All right, and so we've got two integrals here. So technically this is like x goes from minus infinity to 1, and y goes from minus infinity to 2 dy, and then you would put the whole function in here, f of x and y. But of course that f is going to clip those integrals so that they only go from 0 to 1 and 0 to 2. So we'll do that. And the integrand is then x plus y times 1/15. Okay? So 1/15 is out in front. Leave the x integral alone for now. And perform the y integral. And so we get 2x plus 1/2 2 squared, which is 4. Right? So that whole quantity is then 2. And so we get then 1/15. I can do the x integral, and I get 2 times 1/2 1 squared. Plus, now that half of 4 is 2, and times the x, do the x integral, and you get 1. Alright, so it's 1/15. And so I've got 1 plus 2. And so this is 3/15. Okay? I hope that the integration notation is okay with you. I find it useful for the following reason. I've got the letter y right next to its boundaries. When you put the dy all the way over here like this, I always get confused. I've got my integrations, I've got like, these integral symbols over here on the left, like sort of disembodied from the dx and the dy, and it's easy to lose track. You're constantly looking back and forth all the time. I find this a more convenient way to work. I didn't invent this. A lot of people use this. All right. And now we'll just do one last definition here. So if you have the probability density function, the next thing we would normally do is introduce, for the one-dimensional case, the cumulative distribution function. And we'll do that here too. So I think this is just a parenthetical thing in the notes, but I thought I'd make a separate definition out of it. So let's say x and y are continuous random variables. With a joint PDF. Then the joint cumulative distribution for x and y. Is again capital F of x and y, and it has this definition. So this might not be what you would have thought. I don't know. It looks okay to me though. Integrate from minus infinity up to x. I'll go for the old school notation here. And integrate from minus infinity up to y. F of u and v. And then see, we've got to get these in the right order. So this is dv du. Right, so the v is the y integral and the u is the x integral. So in my notation, if you want to see, I think this is easier. Minus infinity up to x du, minus infinity up to y dv, and then f of u and v. So there's just like sort of fewer hurdles for writing this down, less room for confusion. And then I'm just going to point out a thing you can get from the fundamental theorem of calculus. So if capital F is the integral of little f, then little f is going to be some kind of derivative of capital F. And so I'll just write this down. Oops. It's the partial derivative with respect to x, partial derivative with respect to y of f, x, and y. So this is from the fundamental theorem of calculus. Okay. All right, so now we're going to introduce the marginal probability density functions, much like we did for the discrete case. So these are marginal PDFs. And these really do follow kind of the same thing. You can almost guess what this definition is, probably. So we'll just jump right into the definition. So if x and y are continuous random variables, with a joint PDF, in the usual notation, then the marginal PDF for x is the following. We'll put a subscript of x and this will be an integral over the y values of the joint PDF. Like that. So that's probably what you would have expected. And then similarly, sorry. The marginal PDF for y. It looks just like that. We integrate over x, eliminate x. Yeah, like that. All right, and so for what we're going to try now is for the same example that we were doing, we want to find the marginal distributions, the marginal PDFs, right? So this is I should just hide. I gotta get in my habit here. So this is the marginal PDF for x, and this is the marginal PDF for y. This is just definition of those things. All right, so we'll do our little example. So for the same example that we just did, so for previous example, find the marginal distribution. So find f sub x of x and f sub y of y. Oh, and I should add, these things, it's important to add this. This is only... Oh no, we're okay, we're okay. Sorry, I thought I had to add a condition there, but everything is okay. Back to normal. All right, so let's look at these marginal distributions. So f sub x of x, so we're going to integrate over y. And of course the integral gets clipped right away to the range of 0 to 3. And we've got 1/15 x plus y. Right? And the integral over x, nothing happens to the x, so we get 3x. And then the integral over y, we get 1/2 3 squared, which is 9. All right, so we get 1/15 of 3x plus 9/2. Yeah, that's the marginal distribution for x. All right, and for y, it's just a different integral. So the integration then it gets clipped from 0 to 2, 1/15 of x plus y, and we're integrating over x. Right, and so this is 1/15 times 1/2 2 squared, which is 4, plus 2y. So in other words, 2/15 times 1 plus y. All right. And for both of these, so otherwise, yeah, so we have to be a little bit careful here. This isn't exactly true, right? What's not, so we haven't said anything about what is the value of x just yet, right? So if you look at this, right, this function here, it's not always this for any value of x and for y between 0 and 3. It's only for, so we'll say for x in between 0 and 1. Or sorry, 0 and 2, whatever it is. Let's see, let's look at my notes here. 0 and 2. And then we got to duplicate that like all the way down the line. Oops. Yeah. And similarly for the y, this is not what f of xy is always equal to. Even if you just restrict x to be between 0 and 2, you have to also restrict y to be between 0 and 3. So we'll say for oops, and it's not x we're talking about here. It's y. Right? And so we'll copy this again for all these remaining lines. And I think we actually have to add a little bit more, right? So, sorry, this is all this repair stuff. So this is what it is for x in between 0 and 2. If x is not in between 0 and 2, then it's 0, right? So we'll say otherwise 0. right? And then that should be repeated here, 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 and here, right? So these marginal distributions, they're not suddenly evaluatable for all different. I mean, they're all piecewise defined, so that they're zero outside of the disallowed regions for x and y. I hope that's clear. All right. Now we're going to introduce conditional probability density functions. For the bivariate case. And for this guy, the definition is again, it's very much just patterned off of what we saw for the discrete case. So let's define. So we're going to use the same thing. X and y are continuous random variables. Oops, CRVs, sorry about that. With the joint PDF F. Right. Then we really have to make two different statements here. So there's the conditional probability for x given y and for y given x. All right, so let's do these. So the conditional PDF for, we'll start with for x given y. Is the following. Oops. Capital Y down there. And that's, sorry, given Y. And so this works just like we've done before. So it's the joint distribution on top. And then underneath the marginal. And this is only okay, you can only use this definition when the marginal distribution is not zero. Which it can be zero, as we've just seen, right? So if you go back up here, this marginal distribution is only this for these conditions, and otherwise it's zero, right? So there definitely are places where the marginal distributions are zero. All right, so that's the conditional distribution for x given y. So we're really defining kind of two things here. The other one is for y given x, but it looks the same. And it's f sub y given x. And the ratio is almost the same, but with x underneath. Oops, and that's a little x underneath there. And again, this is only for places where the marginal distribution for x is not zero. All right, so that's our definition. It's really, those two definitions are really kind of the same. And we'll try another example using, again, carrying over from our previous example. All right, so little example. So for the previous examples, find these marginal distributions. inverse. Oh man, I've messed this up. This is y given x and x given y. There we go. All right. So I'm going to start off with I'm going to do these in the opposite order that I just wrote them down. So I'm going to look at the conditional distribution for x given y. Right now, if you go back up here and look at this, so for x given y, so I'm going to do this guy. I got to only look in places where y is not where the marginal distribution for y is not 0, right? So I got this formula here, but only for places where y is not 0, right? So for y in between 0 and 3, we have the following. So we have fx given y so it's f of xy over the marginal distribution for y. And I'm just going to copy those. Right, so the joint distribution I've got somewhere up here. I'll just write it down. I remember it. Sorry about that. So it's a 15th x plus y. And the marginal distribution I don't remember. We did work it out though. Here it is. Just steal it. So it's 2/15 times 1 plus y. Put that down there. And then when you tidy that up, the 15ths go away, and you get 1/2 x plus y over 1 plus y. Now, this is what it looks like when x is where? In between 0 and 2. Otherwise, it's 0. Right, so we'll put that there as well. And you should be able to see where did that actually happen. So that happened when I changed this guy into this, right? Because this thing had like a piecewise definition. This one has a piecewise definition too, but it's not, we don't keep track of that. We just force it to be in the place where it's non-zero. So its piecewise definition doesn't influence this one. Hope that's clear. I think that the notes are actually a little bit clumsy with this. They just insist that this thing is given by this thing for both these conditions. And that's a little too strict because you can, you do have to enforce this and you still get this answer, but you can still have this answer for any x's. X doesn't just have to be in between 0 and 2. Sorry, you don't get this answer, but you get 0. All right, so this conditional probability can be 0. So it's a sort of a fine point. The notes are a little bit overly strict on this condition. So again, we'll do the other conditional distribution. So for x in between 0 and 2, then this guy is again, so it looks just like the same. I'm just going to write it out so I know what to steal from above. Right? And the numerator, again, I know that's the same. So that's a 15th x plus y. If, so I got to put this for y in between 0 and 3. and then 0 otherwise. And then the denominator, I'm going to go take the marginal distribution for x, which we worked out way up here. And it's here. There we go. We'll paste that there. It's getting a little crowded over there. Oops. Yeah, getting pretty crowded. Let's do this. Let's move this guy over a bit. Okay. We can make the little fraction line bigger. It's getting pretty crowded. Okay. And then we can tidy this up. So the 15ths go away. And we just get the ratio x plus y over 3x plus 9/2. And that's it. But then there's this condition for y in between 0 and 3 and 0 otherwise. Okay, I hope you enjoyed that lecture. We're most of the way done introducing the topics that you might kind of think of as relatively predictable for the bivariate distributions. So for example, the bivariate probability density function that we talked about today. In the next lecture, we're going to introduce topics that are maybe a little less easy to guess at. We're going to talk about independence of pairs of random variables in a way that allows us to kind of quantify their independence. So we'll introduce covariance and correlation. I'll see you then.